Hi there, I'm Josh Finn from J&H Aerospace. This is the trimming video for the new 2024 Tech Flyer for Technology Student Association High School Flight. In this video, we're going to demonstrate how to trim this airplane for proper flight, how to make it perform well, and how to get the most out of it. There will be a little bit left for you to develop further, but this is the basic instructions you need to get the airplane flying past 1 minute or so that you can get the airplane to operate in a good and reliable manner. So I highly recommend that you follow the instructions and the procedures that we show here, because they will prevent a lot of pitfalls that you would otherwise run into and that are typical in this event. So with that, we will show you some of the tools and get started. Alright, so we're going to show you a couple of tools, but I want to point out we're assuming you already have rubber motors that are made to the 1.5 gram maximum. You need to understand in advance these rubber motors are disposable, so you should be expecting to break them during standard usage. You know, when you show up to a contest, you should not bring one rubber motor. You should bring lots of them and expect to break for whatever number of flights you're going to make. Expect to need at least half that number of rubber bands. You're going to break these, so don't show up with just one. You need to have them made up in advance. Now, this rubber motor has plastic O-rings like these. You can also use rubber ones. These are very important. Do not expect to have good success if you aren't using O-rings. Now, this is a silicon-based rubber lubricant. This is Molykote 33. There are several other products like this. You can use Armor All in a pinch, since it's available at typical local stores. There is a silicon lubricant that we offer that is as good or better than this material, and so there are lots of options in that regard. Now, this tool right here is a fairly advanced winder. This one has a built-in turns counter. You do not need this level of technology to be successful, but you do need a winder. This is a manual torque meter. This is, analog, mechanical one. This is a digital torque meter. Either of these will suffice for your typical usage in TSA. You do not absolutely have to have a torque meter to fly successfully, but in order to get good information, you really need a torque meter. In a pinch, let's say you show up to a contest and you've left this behind or what have you, a paper clip or something to secure the rubber motor to a table leg or something is a good idea as an option, but you need to have some system where that you can at least have the back half of the rubber motor tied down to a solid object, and let me explain what I mean by that. Some solid object that I can pull against that will stay put is absolutely critical, because you're going to stretch this out and wind it. You want to wind off of the airplane, because if you wind on the airplane, this breaks, it smacks the airplane and tears it up. The other thing is you've got landing gear hanging down and whatnot, so while you're winding, if you're winding on the plane, you can damage the airplane, and now you're wasting valuable time trying to repair your airplane instead of getting flying done. In addition, every time you repair your airplane, you're adding weight to it. Now, having established all of that, we're going to head towards trimming the airplane, and so we're not going to wind it up yet. So now we have assumed that you've showed up to your flying site with your airplane in a box, you have unboxed it, and have installed your parts like so. We're going to take a rubber motor that is ready to go, and we're not going to wind it up. Instead, we are going to find a way to tension it on the airplane. Now, since this is 1/16 inch rubber, it's relatively thin and long, so what we can do is we can double it up on the fuselage like this. We're not going to use this to power the airplane. Instead, we're constraining the rubber band on the airplane. Now, you can slide your wing fore and aft, forwards or backwards, to balance the airplane within reason. So if you end up with your wing way back here to balance the airplane, that means you probably are going to have to add clay to the nose. On the other hand, if you have to slide it very far forward, there may be something else wrong elsewhere on the airplane. This is about where this one needs to balance. I'm balanced, so that puts me with my center of gravity 1 inch behind the trailing edge of the wing. This is found to be a good balance point for this airplane. And it's allowed to balance that far back because we have a very large tail surface. Now, if you will notice, your tail mounts in so that it is angled upward from the rest of the fuselage. The wing is actually mounted very slightly positive because this front post is slightly taller than the rear post. So we have a positive angle here, we have a negative angle here, and that means that if this wing is level, then the tail is angled slightly down, so the trailing edge is lower, the leading edge is lower than the trailing edge, which means that the airplane tends to pull up. So if my center of lift with these two flying surfaces is somewhere back here, and I've got a center of gravity up here, that means the center of gravity pulls the airplane down relative to the center of lift. But since this tail is at a negative angle to the wing, it will pull it out of that dive and tend to bring the airplane back to a nose level attitude. That's very important. The next thing to check your airplane for after you've verified that you have that good angle, because this tail boom is seating correctly and your tail is not bent or warped or whatever, is to check the warps on the wings. So if you have a wing that is twisted like this, you're going to have to find a way to correct that. If this wing is twisted this direction, you're going to have to correct that. Now, a little bit of very slight twist in this direction, which rolls the airplane to the right, is useful. And we're talking, about this much right here, just a tiny little bit, about 1/16 of an inch at most. Check that your tail is not overly twisted in one direction or the other, so that the collective angle has the airplane positive or anything of that nature. Once you've got the airplane balanced an inch behind the wing with everything in place, then we can proceed further. So I'm going to show you two possible outcomes with your flying and with your test glides before you start powering the airplane that will give you an idea of what corrections to make. All right, to do our flight trimming on this airplane, the first thing we want to do is a set of test glides, unpowered. That's why we've balanced the airplane as we have. So to test glide the airplane, you don't chuck it up like this. You don't drop it like that. You want to point at a point on the floor about 20 feet in front of you, and you want to slide the airplane. You don't want to throw it, you want to just slide it into the air. So we're aiming at that point, and what we're going to look for is to see the airplane come out, and you can see the airplane is stalling. So let me explain, we'll get the airplane and I'll explain how to fix that. All right, stalling means that the negative angle between the wing and the tail is excessive for the center of gravity location that we have. So now what we have is the airplane is pitching up like this. So it's pitching it up too much. The wing stalls up here. This is at a lower angle, so the wing stalls first. It drops down, which is a positive recovery. We want that. But then the airplane pitches back up into a secondary stall. So the way that we can fix that is to reduce this angle, and we do it by raising the leading edge of the tail boom. So what we can do is we can pop it up, we can take a small little piece of wood like this one, and we can drop it into this slot so that it just covers the front of the tail boom. If we drop that in there, we should see less stalling. You can still see we have a little bit, but it has been reduced, so you would want to add another shim in there. All right, so if the shim that you've placed in here is thick enough, you can stack another shim on top of it, as far as wide enough so that they'll actually stack, or you might want to cut a thicker shim and place it on there. But either way, the point is that to further reduce that stalling, we need to place another shim in so that we can further reduce this angular differential. And now when we do that, we get a very, very smooth, steady glide like that. Now, you notice there was still a slight stall in there. That's because I actually threw the airplane a little bit too hard. So that's something you have to bear in mind. You need to equalize your throw to the actual speed the airplane wants to fly in order to get a steady glide. Another possible outcome from your test glide is that the airplane does the opposite. We saw stalling, but you may say, I didn't get that, I got something different. Maybe you got that. That is called a dive, and it is the opposite of stalling, and it is solved the opposite way, as I will now demonstrate. So if your airplane is diving in, what you would do is instead of putting a shim at the front, you would put it at the back. So with the shim under the back, at the back of this slot, now we will see that the airplane is able to assume a very nice glide. Now, it's very important that you go small shims at a time so that you don't overkill, because I could have very easily pushed that scenario right there into the airplane stalling, and vice versa. So, small adjustments are all that's necessary. All right, now there are two other scenarios that you could have run into that are also important. Let's say that the airplane in its diving was rolling in to the left. If it's rolling in to the left, then that means that you don't have enough twist here, or that your tail possibly is crooked. You need to correct that. So you would want to add some twist to correct for that. Alternatively, the airplane may be rolling into the right, which would mean you have either too much twist here or too much twist here, and you will need to relax that to compensate. Now, one important thing to notice, going back to a stabilized glide pattern, is what we were seeing in terms of right to left behavior. We have our pitch behavior fixed now. Now we need to look at the airplane's roll and yaw behavior. So watch again what the airplane does when I let go of it. Okay, so what we saw was that when we launched the airplane started gradually turning to the right. It did so in a stabilized fashion, and outdoors that would be fine, but we're flying indoors and we need the airplane to maintain a stabilized pattern throughout its flight, keeping it off the walls. This airplane is naturally going to pull to the left some amount under power, so that would cause a reversal of turning direction in flight, which would cause the airplane to crash into the walls. So what we're going to do is we're going to force the airplane into a left turn. So you should check first to verify that this side of the tail, the right side, is not higher than the left, as you see here. In our case, it's about flat. Now I can twist the tail boom a little bit to add some left turn. You can see how now it's slightly higher, but as you're about to see, that may not be good enough. So we can see the airplane is gradually turning to the left, but it's not turning enough. That would not keep it off the walls in this gym. That's about a 200-foot diameter circle, and we've got about a 75-foot wide gym. Now, it would be reasonable to assume that I could tilt the tail further and I could force that left turn. However, as we increase this angle past about 5 degrees, we start seeing greater and greater losses of performance. In order to correct, since we're saying we're going to lose performance by tilting the tail more, we are going to add some rudder trim. So the way that we're going to do that is we're going to bend one of the rudders off, and we can do this by, and you can hear it cracking a little bit. You can see now it's deflected to the side. Now I've chosen to do this on the left side. You could do it on the right side. You could do a little bit of both. It's your choice, not a really big deal. You can see, like I said, I've cracked it. If a piece breaks off, just glue it back on, it's fine. That's part of the process. You have to be willing to crack and break things a little bit to get it working. Just like if the wing is warped, you may have to crack it and break it loose and re-glue it in correct alignment. But now, with that little bit of deflection, let's see what the airplane's response is. So you can see now I have a very, very strong and consistent left turn behavior out of the airplane. We may want to tighten that up a little bit more, so we're going to deflect the rudder on the right side a little bit as well, so that we can tighten that turn up just a little bit more. All right, so I'm going to take the rudder on the right side, and I'm going to bend in a little bit on it as well, just like so. And now, with that amount of deflection on both sides, we should be able to get a very tight turn that would allow this airplane, if it dead sticked up at the ceiling, to circle around safely inside. And you can see we've got very, very nice turn now. All right, now we have the airplane gliding successfully. Now you might think, since this airplane has landing gear, has to take off from the ground, that the immediate next step is to wind this up and let it take off from the ground. That is a pitfall because it will usually lead to not being able to get the airplane to fly. We first have to get the airplane to fly from a hand launch before we can go to taking off from the ground, because if the airplane just stays on the ground, you have no idea why it just stayed on the ground. If the airplane takes off from the ground and stalls and immediately falls back, you still have no idea why, because the airplane is engaging ground effect, because it behaves differently when it's close to the ground, and so it's harder to diagnose what's wrong with the flight behavior. So we're going to wind in enough power to get a slight cruise, and we're going to evaluate what's going on there. What we're going to do is we're going to load this motor on. So we load it by the O-ring onto the hook on our torque meter, and then we load the other end onto this winder. Now, again, this is a digital winder. You don't have to have this level of technology to work with the airplane. The red winders that we sell will work fine, and you have to count winder cranks. They are 20-to-1 ratio, just like this one. So you would have to, for your number of turns that this motor receives, you have to divide by 20 so you know what you're putting in. This rubber motor, when it's broken in, will take about 2,200 turns. That's a long time to hand wind, so you need a winder of some sort. It doesn't have to be fancy, it doesn't even have to be our red winders, but you must have a winder if you're going to be successful. Hand winding the airplane simply does not work. Again, you need to have something to attach this other end to. The O-rings are very critical because they allow you to transfer a wound motor much more easily without losing turns. So what I'm going to do is I'm going to stretch out just a small amount, and my torque meter was zeroed at 0, and I want to wind up to about 0.25 on this torque meter. So I wound in half of my turns at full stretch. I'm winding in the other half as I work my way in, and I'm at 700 turns now. Now this is another thing, I'm able to lock this winder in place. Any kind of little box and something to secure the handle of the winder will be sufficient. You don't have to have, again, this level of technology, but this is useful for our demonstration purposes. I'm at 0.25 on my torque meter. Braking torque for this rubber motor on this torque meter is usually around 0.7 to 0.8 on this torque meter. If you have a digital torque meter, that's between 0.7 and 0.8 inch ounces. Now my landing gear, I've put my landing gear on the left side of the airplane, so I have to load the rubber motor from the right side. So what I'm going to do is I'm going to grasp this O-ring. I grab the rubber motor right behind the O-ring so I have enough O-ring exposed to be able to slide it onto my propeller shaft, just like that. Now I have to be careful to not smack my airplane against anything, drag the landing gear too heavily on the rubber motor, etc. And now I can disengage the back O-ring from the torque meter, and I can slide it onto my rear hook. Very important, I have placed the knot in the rubber motor about here. We don't want it in the front half in case it beats against anything, and we don't want it in the vicinity of the landing gear. Right here, if you have a small knot, it will clear the motor stick and it won't cause any problems. Now, to launch this airplane, what I do is I let go of the propeller and then I slide the airplane into the air. I'm not throwing it, I'm not dropping it, I'm just sliding it into the air just like I'm doing a test flight. So if I stand here, I know that this airplane should circle to the left, so I'm going to launch across from the middle of the building so that I can try to center the circle in the ring. So I let go of the propeller, let go of the plane, and we actually gave it a little bit more power than necessary because the airplane is flying. And we can see the rubber motor is fully unwound and the airplane is working its way. Okay, your airplane may not have done what mine did. Mine is behaving well because once I'm transitioning from a well-established glide to power, excuse me there, everything worked well. Your airplane may have rolled in to the right, it may have stalled, may have dove. If your airplane dove, you are going to have to add in more incidents on your tail. If the airplane, on the other hand, is stalling, it's probably going to indicate that there's an issue up front. So if it is stalling, you would actually need to cut the front of your fuselage and re-glue it so that the propeller is pointing down slightly, so that the propeller pulls down a little bit to keep the airplane from pitching up into a stall, hanging like this and falling back to the floor. That's called down thrust. It's a trimming technique, and yes, you actually have to cut the nose so that you can angle it down. So down thrust is one method for addressing if the airplane is stalling under power, but it's gliding well. Now, another scenario you might see is that the airplane takes off and it flies straight or heads off to the right. In that case, you will want to bend your nose bearing, so you would grab this part right here and you would twist it this direction. You don't bend the wire part at all, you only bend the plastic part so that the propeller points a little bit to the left, and that will get you into a nice turn. On the other hand, if your power pattern, your setup that got you a nice turning glide causes the airplane to pull very hard into the left, you either need a little bit more wing twist, and you can try cracking and gluing in a tiny little bit more wing twist. If that doesn't work, then you will need to twist the propeller so the propeller points a little bit to the right. Now, I don't mean bending it so it's offset to the right, I mean it's actually you're twisting to point to the right, and that'll help it straighten out and fly a wider pattern. In our case, it looks like the airplane is performing just fine, so we're going to proceed on from there. All right, so we know that about 0.25 inch ounces on this torque meter is getting us most of the way to the ceiling. So we're going to say about 0.3, a little over 0.3 is about the maximum we can safely use in this flying site. So I'm going to wind this airplane much more aggressively this time. If you remember, we only put in 700 turns last time. This time, I'm going to go up to 1,000 turns, and now I'm going to wind in my remaining turns as I work my way in. This puts me at just shy of 1,900 turns at 0.5 inch ounces. This will put me into the ceiling and I'll lose my airplane. So now what I'm going to do is I'm going to make use of something called hysteresis in the rubber motor, and I'm going to back wind. And now I'm down at 1,740 turns. I'm going to go even a little bit less just to be on the safe side. 1,699, 1,700 turns at 0.25 inch ounces. So we're at the same torque as before with over twice as many turns. Now the motor is much tighter now, so it's a little harder to load it onto the airplane. But if you pay close attention, you can see I'm having a little bit of trouble getting off the hook here. If you have an assistant, have them hold that hook and kind of help you stabilize it. And now we're going to let the airplane take off from the floor. So what I do is I let go of the propeller and then the plane. Propeller, plane. And now the airplane is making a liar of me because it's probably going to hit the ceiling. So in this case, you would want to back off that torque considerably more to prevent your airplane from getting stuck or hitting an obstacle and ruining the flight. As you can see, that's the type of behavior that you have to deal with. And so now, since the airplane is hitting obstacles, it's shifting around, and eventually it's probably going to hit a wall, and it will end the flight prematurely. As you can see, that upcoming failure mode appears to be about to occur, and there we are, end of flight.
No 10-second bonus points either.
All right, so at this point, we've shown you the techniques to get the airplane flying. And I think at this point you've seen what's necessary. So you want to back off that torque probably down to about 0.2 to keep the airplane out of the ceiling and have a successful flight. You could also experiment with possibly twisting the blades to increase their pitch so that you could slow the propeller down somewhat. But I hope that will provide enough to get you flying successfully with your TechFlyer. Please contact us if you have any questions. Comment below what you're running into, what things you've seen, and so we can get a conversation going on ways to solve additional problems. Don't forget your documentation is for your portfolios. It is vitally important to your scores in TSA flight, and we hope to see you at the contests. Hi, I'm Josh Finn. This is Hope. We are J&H Aerospace.
If you like this video, hit the like button.
Also, how about subscribe to our channel and check out jhaerospace.com for new free flight products and all of the tooling that you'll need to build them.
Thanks for watching.